For millennia, human beings have gazed upward at the night sky with wonder and longing. Our ancestors looked at the stars, moon, and sun, believing they were close enough to touch celestial companions hanging just beyond our reach. They wove stories around these luminous points of light, creating myths and legends that bound Earth to heaven. The stars were gods, ancestors, guideposts for navigation, and symbols of humanity's deepest aspiration, asterisk. But as our understanding of the universe evolved, so did our humbling realization of just how vast the cosmos truly is. We discovered that those twinkling lights are not nearby companions, but impossibly distant suns, separated from us by gulfs of space so enormous that our minds struggle to comprehend them. The nearest star to our solar system, Proxima Centauri, lies approximately 40 trillion kilometers away. To put this in perspective, if we could build a highway to this star and drive at 100 kilometers per hour without ever stopping, the journey would take more than 45 million years, asterisk. Even our fastest spacecraft machines representing the pinnacle of human engineering would require over 10,000 years to reach even our nearest stellar neighbor. The dream of exploring the galaxy, of becoming true citizens of the universe rather than residents of a single pale blue dot, seems impossibly remote when confronted with such staggering distances, asterisk. Yet throughout history, humanity has consistently achieved what once seemed impossible. We have conquered diseases, split the atom, walked on the moon, and built machines that can think. The stars may be distant, but they are not necessarily unreachable. To make them accessible, however, we must do something that physics tells us is impossible. We must find a way to travel faster than light itself. Asterisk. This is the story of that quest to journey through cutting-edge physics, revolutionary theories, and bold experiments that are challenging the very foundations of what we know about the universe. It's a story about scientists who are learning to bend space, create exotic forms of energy, and perhaps even rewrite the fundamental laws of nature. It's about humanity's refusal to accept limitations and our relentless drive to explore, discover, and push beyond every frontier. Asterisk # Chapter 1, Understanding Light, the Universal Speed Limit. Asterisk ##, The Mystery of Light's Nature. Asterisk. As a child growing up in Mississippi, physicist Sean Carroll would spend countless evenings sitting beside campfires, mesmerized by the dancing flames. He would watch the firelight for hours, pondering a question that has fascinated humans for millennia. What is light made of? How can something appear so solid in one moment, bright, tangible, almost physical, and then vanish into nothing the next instant? Asterisk. This childlike wonder about light's mysterious nature is something that Sean Carroll carried with him into his career as a theoretical physicist at the California Institute of Technology. Even today, with decades of scientific understanding behind him, he remains fascinated by the peculiar properties of light and the fundamental role it plays in the structure of our universe. Asterisk. Light travels at approximately 299,790 kilometers per second, or about 1.07 billion kilometers per hour. This incredible velocity means that light can circle the Earth's equator more than 7 times in a single second. To put this in more relatable terms, if you could travel at the speed of light, you could go from New York to Los Angeles in less than 0.02 seconds. You could reach the moon in just 1.3 seconds and arrive at the sun in about 8 minutes. Asterisk. Light moves roughly 1 million times faster than sound. When lightning strikes in a distant storm, we see the flash instantly or near instantly, given the finite speed of light. But we must wait for seconds or even minutes to hear the accompanying thunder. This dramatic difference in speed explains why we see fireworks explode before we hear the boom, and why we can see a drummer's sticks hit the drums before the sound reaches our ears at a distant concert. Asterisk. But light's incredible speed is not its only remarkable property. Light also represents an absolute cosmic speed limit. Nothing in the universe can travel faster than light. This is not simply a practical limitation based on our current technology. It is a fundamental law woven into the very fabric of space and time. Asterisk ##, the peculiar behavior of light. Asterisk. To understand just how strange light's behavior is, imagine conducting a simple experiment. Suppose you're driving down a highway at 50 kilometers per hour, and you throw a ball forward at 30 kilometers per hour relative to your car. Common sense tells us that the ball is now traveling at 80 kilometers per hour, relative to someone standing on the side of the road. We simply add the velocities together. 50 plus 30 equals 80. This is how velocities work in our everyday experience. Asterisk. Now imagine you're driving backward at 50 kilometers per hour and throw that same ball forward at 30 kilometers per hour relative to your car, to a stationary observer on the roadside. The ball would appear to be moving backward at 20 kilometers per hour. 50 to 30 equals 20. Again, this matches our intuitive understanding of how motion works. Asterisk, but light doesn't follow these intuitive rules. If you're driving forward at 50 kilometers per hour and shine a flashlight beam ahead of you, you might expect that the light would travel at the speed of light plus 50 kilometers per hour. But this is not what happens. The beam of light travels at exactly the speed of light, no faster, no slower, regardless of how fast your car is moving. Asterisk, this is profoundly counterintuitive. Whether you're standing still, driving forward at high speed, or even flying through space in a rocket ship at half the speed of light, any beam of light you emit will always move away from you at exactly 299,790 kilometers per second. You cannot add to or subtract from light's velocity through your own motion. Asterisk. This bizarre property of light led Albert Einstein to one of the most revolutionary insights. In the history of physics, space and time are not fixed, absolute quantities. Instead, they are flexible and relative, interwoven into a single fabric called space-time. What seems like pure space to one observer might be a mixture of space and time to another observer moving at a different velocity. Asterisk hash hash hash. E equals mc, the most famous equation in history. Asterisk Einstein's realization that space and time are interconnected led him to perhaps the most famous equation ever written. E equals mc. This deceptively simple formula reveals a profound truth about the nature of reality. Energy and mass are not separate things, but different forms of the same fundamental quantity. Asterisk in this equation, E represents energy, M represents mass, and C represents the speed of light. The equation tells us that mass can be converted into energy as happens in nuclear reactions and inside the cores of stars, and that energy can be converted into mass as happens in particle accelerators. The speed of light squared c squared is the conversion factor between these two forms. Asterisk, but this equation has profound implications for space travel. When we add energy to a rocket to make it go faster, we're not just increasing its velocity, we're also increasing its mass. The faster the rocket goes, the more massive it becomes, and the more energy is required to accelerate it further. As a rocket approaches the speed of light, its mass increases dramatically, requiring ever more colossal amounts of energy to continue accelerating. Asterisk, imagine trying to push a shopping cart that gets heavier the faster you push it. At first, it rolls along easily, but as you speed up, it becomes harder and harder to push. Eventually, it becomes so heavy that no matter how hard you push, you can barely increase its speed at all. This is essentially what happens when an object approaches the speed of light. Asterisk, according to Einstein's theory of relativity, reaching the speed of light would require an infinite amount of energy. Since the universe contains a finite amount of energy, this means that no material object can ever reach the speed of light, let alone exceed it. The speed of light is thus an absolute barrier, a cosmic speed limit that cannot be broken through conventional means. Asterisk hash hash hash. The tyranny of distance. Asterisk, this cosmic speed limit creates what we might call a cosmic prison for humanity. Our galaxy, the Milky Way, contains between 100 and 400 billion stars. Many of these stars have planets, and some of those planets may harbor life. The universe beyond our galaxy contains hundreds of billions of additional galaxies, each with their own complement of stars and planets. The cosmos is vast, almost beyond comprehension, filled with wonders that we can observe through our telescopes, but may never reach. Asterisk. Even traveling at the speed of light, which Einstein tells us is impossible. For any material object, journeys to even nearby stars would take years or decades. Proxima Centauri, our nearest stellar neighbor, is 4.4 light years away, meaning it would take 4.4 years to reach it if we could travel at light speed. The center of our galaxy is about 27,000 light years distant, and the nearest large galaxy to our own, the Andromeda Galaxy, lies 2.5 million light years away. Asterisk, at our current technological level, these distances might as well be infinite. The Voyager 1 spacecraft, launched in 1977 and currently the most distant human-made object from Earth, is traveling at about 61,000 kilometers per hour, less than 0.006% of the speed of light. At this rate, Voyager 1 would take more than 70,000 years to reach Proxima Centauri, if it were headed in that direction, which it isn't. Asterisk. So humanity faces a profound dilemma. We have built telescopes that can peer billions of light years into space, showing us galaxies as they appeared when the universe was young. We have discovered thousands of exoplanets orbiting distant stars, some of which might be similar to Earth. We have developed a deep understanding of the cosmos and our place within it. But all of this knowledge only emphasizes how isolated we are, trapped by the tyranny of distance and the cosmic speed limit. Asterisk unless we can find a way around Einstein's prohibition, the stars will remain forever out of reach. We will be able to observe the universe, but never to explore it. We will remain stuck on our single planet, looking outward at wonders we can never touch. Asterisk, but what if there are loopholes? What if the cosmic speed limit can be circumvented, if not directly broken? This is where the story takes a remarkable turn, as physicists have begun to identify possible ways to achieve faster-than-light travel, without actually violating Einstein's fundamental insights. Asterisk hash hash. Chapter 2, The Warp Drive Bending Space to Beat the Speed Limit. Asterisk hash hash hash. A Mexican physicist's revolutionary idea. Asterisk Miguel Alcubierre is a theoretical physicist from Mexico City, who has proposed one of the most intriguing solutions to the problem of interstellar travel. In 1994, while working on his doctoral thesis, Alcubierre published a paper that showed how a spacecraft might achieve faster-than-light travel, without actually violating Einstein's prohibition. Asterisk Alcubierre's key insight was this. Einstein's theory says that nothing can move through space faster than light, but it says nothing about how fast space itself can move. This distinction might seem like a technicality, but it opens up a revolutionary possibility. Asterisk my warp drive is a way to get from one place to another, Alcubierre explains. But it's completely different from how we normally travel. Usually, we move through space walking, driving, or flying. But with a warp drive, we don't move at all. Instead, space itself moves around us. Asterisk hash 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 understanding space-time distortion. Asterisk to understand how this works, we need to think about Einstein's other great insight, that space is not a fixed, rigid framework, but a flexible fabric that can be stretched, compressed, and distorted by the presence of mass and energy. Asterisk we experience one manifestation of this flexibility every day, gravity. Gravity is not actually a force pulling objects together, as Newton thought, but rather the result of massive objects curving the fabric of space-time around them. Earth curves space-time in its vicinity, and objects fall because they're following the curved contours of space. The sun curves space-time much more dramatically, creating a deep well that holds the planets in their orbits. Asterisk Alcubierre realized that if mass and energy can curve space-time, perhaps we could use this property to create a particular kind of distortion, one that would allow a spacecraft to effectively move faster than light, without actually accelerating to such speeds. Asterisk, imagine space as a stretchy rubber sheet. Now place a toy spaceship on this sheet. Normally, to move the spaceship from one place to another, you would have to slide it across the surface, and the faster you slide it, the more energy you need to expend, just as Einstein's equations predict. Asterisk, but what if instead of sliding the spaceship across the sheet, you could manipulate the sheet itself? What if you could contract the sheet in front of the spaceship, bringing your destination closer, while simultaneously expanding the sheet behind the spaceship, pushing your starting point farther away? The spaceship wouldn't move at all relative to its local patch of space-time, but it would end up in a new location, perhaps very far away, without ever having traveled through the intervening space. Asterisk this is the essence of the Alcubierre warp drive. The spaceship would sit inside a warp bubble, a region of flat, normal space-time. In front of this bubble, space would be contracted, and behind it, space would be expanded. The bubble itself would move through space, carrying the spacecraft along with it. But because the spacecraft isn't actually moving relative to its local space-time environment, it doesn't experience the mass increase that Einstein's equations predict for objects approaching light speed. Asterisk hash hash hash. The beautiful loophole. Asterisk what makes this concept so elegant is that it exploits a loophole in Einstein's theory without actually violating it. Einstein's equations tell us that no object can move through space faster than light, but they say nothing about limitations on how fast space itself can expand or contract. Asterisk in fact, we know that space can move faster than light. In the first instance, after the Big Bang, space expanded at rates far exceeding the speed of light. This is the theory of cosmic inflation that we'll explore in more detail later. And even today, distant galaxies are moving away from us at velocities that exceed the speed of light, carried along by the expansion of space itself. Asterisk, the Alcubierre warp drive would harness this property of space to enable faster-than-light travel. A spacecraft could traverse vast interstellar distances in days or weeks rather than years or millennia. The center of our galaxy could be reached in months rather than tens of thousands of years. Even other galaxies might be within reach. Asterisk, we could travel at any speed we want. Alcubierre notes, physics doesn't place any limit on how fast space can be warped. We could contract and expand space at 10 times the speed of light, 100 times, or even 1,000,000 times. The speed limit only applies to motion through space, not to the motion of space itself. Asterisk hash 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 the problem of negative energy. Asterisk, it all sounds almost too good to be true, and in a sense, it is. While Alcubierre's warp drive is mathematically consistent with Einstein's equations, it requires something that may not actually exist, a form of exotic matter with negative energy. Asterisk, to understand what negative energy means, think about normal matter and energy. A cup of coffee sitting on a table has positive energy, it has mass, it has heat. It has the potential to do work. If you could somehow extract all the energy from that coffee, converting its mass completely into pure energy via E equals mc, you would get a certain amount of positive energy. Asterisk, negative energy would be the opposite, a form of energy that is somehow less than nothing. While this sounds like nonsense, quantum physics suggests that such a thing might actually exist under certain special circumstances. Asterisk, the key point is this: to create the Alcubierre warp bubble, you would need to generate a region of negative energy around the spacecraft. This negative energy would create a repulsive gravitational effect, pushing space away and creating the necessary distortion. Without negative energy, the warp drive simply won't work. Asterisk, but does negative energy exist? Most physicists are skeptical. It seems to violate some basic principles of physics, and no one has ever definitively observed it in nature. However, one scientist believes he has created negative energy in his laboratory, and his experiment might just provide the key to making warp drives a reality. Asterisk hash hash hash. Steve Lamoreaux and the Casimir effect. Asterisk. Steve Lamoreaux is an experimental physicist at Yale University who has spent more than a decade investigating one of the strangest predictions of quantum mechanics, the Casimir effect, which appears to generate a force from the vacuum of empty space. Asterisk, according to quantum mechanics, what we think of as empty space, the vacuum, is not actually empty at all. It seizes with activity at the microscopic scale, as virtual particles constantly pop into existence and then disappear again, in tiny fractions of a second. These quantum fluctuations create what physicists call zero-point energy, a baseline energy level that exists even in supposedly empty space. Asterisk. Lamoreaux realized that if he could somehow reduce the amount of zero-point energy in a particular region of space, he would effectively create negative energy. To do this, he used very small metal plates, placed extremely close together about the width of a human hair. Asterisk. Bringing these plates so close together and keeping them parallel at almost atomic distances was extraordinarily challenging, Lamoreaux explains. But once we achieved it, something remarkable happened. Asterisk, because the plates are so close together, only certain quantum fluctuations can fit in the space between them. Fluctuations with longer wavelengths are excluded. They simply don't have room to exist in such a confined space. But outside the plates, all wavelengths of quantum fluctuation can exist freely. Asterisk, this creates an imbalance. There is less zero-point energy between the plates than outside them. As a result, the normal zero-point energy on the outside pushes the plates together. Or, from another perspective, the negative energy between the plates creates a kind of suction effect, pulling them together. Asterisk, Lamoreaux succeeded in measuring this effect. The force was equivalent to the weight of a single red blood cell in Earth's gravitational field. He notes, it was incredibly tiny, but it was real, and it was measurable. Asterisk, this was a landmark achievement. Lamoreaux had created and measured negative energy, or at least a force arising from negative energy. This proved that the Casimir effect is real, not just a theoretical curiosity. More importantly, it showed that the key ingredient for an Alcubierre warp drive might actually exist in nature. Hash 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 from atoms to starships. Asterisk, of course, the amount of negative energy Lamoreaux produced was minuscule, nowhere near enough to warp space-time around a spacecraft. If we had thousands of these plate assemblies, we could generate a significantly larger force. He notes, but we'd still be far from what would be needed for a warp drive. Asterisk, the challenges are immense. To create a warp bubble large enough to contain a spacecraft, we would need to generate and control enormous amounts of negative energy, perhaps more than exists in the entire solar system. We would need to shape this negative energy into precisely the right configuration to create the necessary space-time distortion. And we would need to do all of this without destroying the spacecraft or creating catastrophic gravitational anomalies. Asterisk, these are not merely engineering challenges. They may be fundamental physical limitations. Some physicists argue that nature has built-in safeguards that prevent the creation and manipulation of negative energy on the scales required for a warp drive. Others maintain that we simply don't yet understand quantum mechanics and gravity well enough to know what's possible. Asterisk. But Lamoreaux's experiment proves an important point. The Alcubierre warp drive is not mere science fiction. It is consistent with known physics, and at least some of its required components can be demonstrated in the laboratory. Whether a practical warp drive will ever be built remains an open question, but it is a question that can now be explored through real experiments, not just theoretical speculation. Asterisk. And as we'll see in the next section, the negative energy required for a warp drive might have another application, one that could provide an even more direct route to the stars. Asterisk hash hash. Chapter 3, Wormhole Shortcuts Through the Fabric of Space. Asterisk hash hash hash. The concept of cosmic shortcuts. Asterisk. While warp drives offer one possible route to faster-than-light travel, science fiction has long suggested another possibility: wormholes, also called Einstein-Rosen bridges. Wormholes are hypothetical tunnels through space-time that could connect distant regions of the universe. Asterisk. Think of the universe as a two-dimensional sheet of paper. If you want to travel from one point on the paper to another, you normally have to traverse the entire distance along the surface. But if you could fold the paper so that the 2 points touch, you could poke a hole through both layers and create a shortcut. A wormhole is essentially the three-dimensional, or rather, four-dimensional equivalent of this shortcut. Asterisk. Stephen Shu is a theoretical physicist at the University of Michigan who has devoted considerable effort to understanding whether wormholes can actually exist and, if so, whether they could be traversable by human travelers. Asterisk. When we think about wormholes, Shu explains, we need to consider the crucial properties, stability and traversability. A wormhole that collapses the instant it forms isn't very useful, and a wormhole that would kill anyone who tries to go through it also isn't much help. Asterisk hash hash hash. The architecture of a wormhole. Asterisk. To understand what a wormhole is, we first need to think carefully about the structure of space. We live in a three-dimensional universe, or rather, a four-dimensional spacetime if we include time as a dimension. But for visualization purposes, let's imagine space as a two-dimensional surface of flexible sheet that can be bent and curved. Asterisk. In science fiction movies and television shows, wormholes are typically depicted as glowing circular portals. A spaceship flies into the portal, travels through a tunnel, and emerges at a distant location. This two-dimensional visualization is reasonably accurate, but it's important to understand what it's really showing. Asterisk. In our two-dimensional analogy, a wormhole opening would indeed appear as a circle on the surface of space, but we actually live in 3 dimensions. So a real wormhole's opening would not be a two-dimensional circle. It would be a three-dimensional sphere, a ball of warp space. Asterisk. If a real wormhole existed in space, Shu explains, its opening might look like a spherical bubble. You wouldn't fly through a flat circle, you would enter a sphere that envelops you completely. Asterisk. The tunnel of the wormhole, the part connecting the two openings, exists outside of our normal three-dimensional space. It's a shortcut through a higher dimensional space that we can't directly perceive. The two ends of the wormhole might be separated by thousands of light years in normal space, but through the wormhole tunnel, they might be only a few meters apart. Asterisk hash hash hash. The engineering challenge. Asterisk. So could we actually build a wormhole? In principle, a cosmic engineer would start by creating the spherical openings in space-time. These would be regions where space is curved so severely that it folds back on itself. Then these two openings would need to be connected through a tunnel, a shortcut through space-time. Asterisk. In theory, this is possible according to Einstein's equations. Space-time is flexible enough to allow such structures, but there's a critical problem: keeping the wormhole open. Asterisk. A wormhole, once created, would have a natural tendency to collapse. The tunnel would snap shut in a fraction of a second, disconnecting the two openings. To prevent this collapse, you would need to prop the wormhole open using some form of matter or energy with very unusual properties. Specifically, Negative energy. Asterisk. This is the same exotic substance required for the Alcubierre warp drive. Negative energy would create a repulsive gravitational effect that would hold the wormhole open, preventing it from collapsing. Without negative energy threaded through the wormhole structure, the tunnel would be unstable and useless. Asterisk hash the stability problem. Asterisk. Assuming we could create negative energy in sufficient quantities, we still face the stability problem that Shu has spent years analyzing. Even if we could prop open a wormhole with negative energy, would it remain stable enough for humans to pass through safely? Asterisk. We proved mathematically that wormholes with negative energy would be fundamentally unstable. Shu explains, they would be incredibly dangerous devices. The slightest perturbation, even a single photon of light entering the wormhole, could cause the entire structure to collapse catastrophically. Asterisk. To illustrate this instability, Shu uses the analogy of a soap bubble. If you carefully blow a soap bubble, it can float serenely in the air, looking stable and permanent. But if you poke it with your finger, it instantly pops. A wormhole would be similar. It might appear stable, but any attempt to send something through it, a probe, a signal, or especially a human being, would be like poking that bubble with your finger. The wormhole would collapse, and anything inside it would be destroyed. Asterisk. This is deeply disappointing from the perspective of interstellar travel. We can't build our own wormholes, and even if we could, they would be too unstable to use. But there may be a way around this limitation. Asterisk hash quantum wormholes. Nature's hidden shortcuts. Asterisk. According to quantum mechanics, the fabric of spacetime at the very smallest scales, distances of about 10 to 35 meters, called the Planck length, is not smooth. Instead, it's a seething foam of quantum activity, with virtual particles and tiny fluctuations appearing and disappearing constantly. Asterisk. Some theoretical physicists speculate that this quantum foam might include microscopic wormholes, tiny tunnels through spacetime that pop in and out of existence. As part of the quantum fluctuations, these quantum wormholes would be incomprehensibly small, far smaller than an atom or even an atomic nucleus. A typical quantum wormhole might be only a few Planck lengths across. Asterisk. If quantum wormholes exist, Shu notes, they would be natural structures rather than artificial constructions. We wouldn't need to create them or stabilize them with negative energy. They would already be woven into the structure of spacetime. Asterisk. The advantage of quantum wormholes is that they might already exist in a stable form. They wouldn't be artificial constructs that we need to prop open. They would be natural features of spacetime that have been there since the Big Bang. If we could somehow enlarge a quantum wormhole to macroscopic size, we might have a stable, traversable tunnel through space. The dangers of quantum travel. Asterisk. However, quantum wormholes come with their own set of problems. The first and most obvious issue is size. How do you enlarge something that's 35 meters across to something large enough for a human or even a single atom to pass through? No one has any idea how to do this, or whether it's even possible. Asterisk. But even if we could somehow enlarge quantum wormholes, there's another serious problem: unpredictability. Quantum phenomena are inherently random and uncertain. We can predict probabilities, but not specific outcomes. Asterisk. Quantum mechanical systems are fundamentally fuzzy, Shu warns. They're random and unpredictable. So if we entered a quantum wormhole, we might experience violent fluctuations during our journey, and we would have no way of knowing in advance where we might emerge. Asterisk. This unpredictability could be catastrophic. Imagine stepping into a quantum wormhole portal and emerging in the middle of the Pacific Ocean, or inside a mountain, or in the vacuum of deep space, without any way to control or predict where the wormhole leads. Traveling through one would be an act of potentially suicidal recklessness. Asterisk. We certainly wouldn't want to enter a tunnel that might drop us at the bottom of the ocean, or on top of a mountain. Shu notes dryly, quantum wormholes might connect any to points in space and time, with no way for us to choose or predict the destination. Asterisk. A glimmer of hope. Asterisk. Despite all these problems, wormholes remain a tantalizing possibility. They are allowed by Einstein's equations. They don't violate any known laws of physics, and they offer the possibility of instantaneous travel across arbitrary distances. Asterisk. If natural wormholes exist somewhere in the universe, perhaps left over from the Big Bang, or created by some exotic astrophysical process, and if we could find them, study them, and somehow stabilize them, they could provide the ultimate cosmic highway system. Imagine finding a natural wormhole, with one opening near Earth and the other near a distant star. Such a wormhole could reduce a journey of thousands of years to a trip of mere seconds. This is, admittedly, highly speculative. We have no evidence that traversable wormholes exist anywhere in the universe. But the point is that they might exist, and that we can explore this possibility through serious scientific investigation, rather than pure fantasy. And even if wormholes prove impossible, there's yet another approach to faster-than-light travel. One that doesn't involve moving through space at all, but rather transmitting information at light speed and reconstructing it at the destination. This is the realm of quantum teleportation. Chapter 4. Quantum teleportation, beaming information across space. The dream of teleportation in science fiction. Teleportation is one of the most iconic technologies. Captain Kirk and his crew members step onto a transporter pad, are dissolved into a beam of light, and instantly rematerialize on a planet's surface or aboard an enemy ship. It's instantaneous, convenient, and perfectly safe. Could this ever be more than fiction? Could we actually teleport matter from one location to another? The physicists, Chris Monroe and Steve Lamoreaux at the University of Maryland, have pioneered techniques that bring us tantalizingly close to this dream. We're working on linking events at two different locations that normally would have no connection whatsoever, Monroe explains. This is the essence of teleportation, making something disappear at one location and reappear at another, without physically transporting it through the intervening space. Understanding quantum entanglement. To understand quantum teleportation, we first need to understand one of the strangest phenomena in physics, quantum entanglement. This is a property of quantum mechanics that Einstein himself found so bizarre that he called it spooky action at a distance. Monroe and Lamoreaux demonstrate the concept with a simple coin flipping experiment. Let's use ordinary coins to show you the difference between normal randomness and quantum entanglement, Monroe says. He and Lamoreaux each take a coin and flip them simultaneously. Heads, tails, they flip again. Tails, tails, as you can see, Monroe notes. With two regular coins, we get completely random results. Sometimes we both get heads, sometimes both tails, sometimes different results. There's no pattern or correlation. Now imagine that instead of ordinary coins, Monroe and Lamoreaux had quantum coins that were entangled. With entangled coins, every time Monroe flips heads, Lamoreaux would flip tails, and vice versa. The results would still be random. Neither person could predict whether their own coin would come up heads or tails, but the two results would always be correlated, opposite outcomes on every single flip. This correlation is not because the coins are communicating with each other, or because one coin is influencing the other. Instead, entanglement means that the two coins share a quantum state. They are, in a deep sense, part of a single quantum system, even if they're physically separated. In the quantum world, this phenomenon is real and has been demonstrated countless times in laboratories around the world. When the particles are entangled, measuring the state of one particle instantly determines the state of the other, regardless of the distance between them. From coins to atoms. Monroe and Lamoreaux have moved beyond mere analogies to demonstrate real quantum entanglement and teleportation using individual atoms. Their experimental apparatus uses atoms of an element called ytterbium, trapped in electric fields and isolated in vacuum chambers. We started with two trapped atoms on opposite sides of the lab, Monroe explains. They're levitated by electromagnetic fields, like a maglev train. They're in a vacuum chamber, so nothing can touch them. They're in complete isolation, which is exactly what we need for our experiment. The researchers used pulses of microwave radiation to encode quantum information onto one of the atoms. This quantum information, called a qubit, short for quantum bit, is the quantum equivalent of the heads or tails state of a coin. But a qubit can be in a superposition of both states simultaneously until it's measured. Next came the clever part. We excited both atoms with fast pulses of light, Monroe continues. This caused each atom to emit a photon, a particle of light. Crucially, each photon became entangled with the internal quantum state of its parent atom. These photons became messengers, carrying quantum information across the laboratory. Monroe and Lamoreaux directed both photons toward the same target. When the photons met and interacted, They became entangled with each other, and this entanglement caused their parent atoms to become entangled as well. Asterisk, the two atoms were never close together. They never saw each other or interacted directly, Monroe emphasizes. But now they were entangled, sharing quantum information. The information we wrote onto the first atom was now also present in the second atom. That's quantum teleportation. Asterisk hash hash hash. The information was never in transit. Asterisk. What makes this truly remarkable is that the quantum information was never in transit through the space between the two atoms. It didn't travel from one place to the other. It simply appeared at the second location because of the entanglement. Asterisk. Einstein described entanglement beautifully when he called it spooky action at a distance. Olmskinc notes, the spooky part is that the correlation between entangled particles is instantaneous. There's no time delay, no signal traveling between them. The connection is, in some sense, outside of space and time. Asterisk. This experiment was a major achievement. Monroe and Olmskinc had successfully teleported quantum information from one atom to another. In effect, they had teleported the atom itself, or at least all of its quantum properties. For the first time, scientists had transmitted matter through space at the speed of light. Asterisk. The good news, Monroe adds, is that this technique can work with more complex objects than a single atom. In principle, we could teleport anything. Hash hash hash. The challenge of scaling up. Asterisk. Of course, there's an enormous gap between teleporting a single atom and teleporting a human being. A human body contains approximately 7 bikisi atoms, that's 7 followed by 27 zeros, or 7 octillion atoms. Each of these atoms would need to be quantum scanned, and its complete quantum state transmitted to the destination, where it would need to be reconstructed with perfect precision. Asterisk. To understand the challenge, Olmskinc uses the example of a cherry pie. This cherry pie exists in a particular state. It contains atoms, mostly carbon and other organic molecules, but they're arranged in precisely the right way to make a cherry pie. Asterisk. He then dumps the pie on a table, splattering it across the surface. Every atom that was in the pie is still here, but it's not a cherry pie anymore because the atoms aren't properly arranged. Asterisk. The arrangement of atoms is what matters. In a cherry pie, in a human body, in any complex object, the atoms must be organized in exactly the right three-dimensional structure for the object to maintain its identity and function. Teleporting something means capturing and transmitting complete information about the position, velocity, and quantum state of every single atom, then using that information to reconstruct the object perfectly at the destination. Asterisk. There are roughly kisi atoms in this cherry pie, Olmskinc notes. To write down all the information about how these atoms are arranged, we would need a number so large that there isn't enough space in the entire universe to write it down. The number would have more digits than there are atoms in the observable cosmos. Asterisk hash hash hash. The fundamental limits of information. Asterisk. The challenge of teleporting complex objects isn't just a matter of technology. It may run into fundamental physical limits. According to quantum mechanics, there is a principle called the Heisenberg uncertainty principle, which states that we cannot simultaneously know both the exact position and exact momentum of a particle with perfect precision. The more precisely we measure one property, the less precisely we can know the other. Asterisk. This creates a profound problem for teleportation. To reconstruct the human body with perfect fidelity, we would need to know the complete quantum state of every atom in that body, but the act of measuring a quantum state inevitably disturbs it. This is another fundamental principle of quantum mechanics. Asterisk. When we measure a quantum system, we collapse its wave function, Monroe explains. We destroy the very quantum information we're trying to preserve. This is called the quantum no-cloning theorem. You cannot make a perfect copy of an unknown quantum state. Asterisk. Quantum teleportation gets around this limitation through a clever trick. The quantum information is never actually measured or copied. Instead, it's transferred from one quantum system to another through entanglement. The original quantum state is destroyed in the process, but that's acceptable. We're teleporting the object, not cloning it. Asterisk. However, this still requires that every atom in the original object be perfectly entangled with a corresponding atom at the destination. For a human body with 7 octillion atoms, this would require creating and maintaining 7 octillion entangled pairs simultaneously. This is so far beyond our current capabilities that it's difficult even to imagine the technology that would be required. Asterisk hash hash hash. The philosophical implications. Asterisk. Even if we could overcome all the technical challenges, Human teleportation would raise profound philosophical questions. Suppose we successfully scan your body, transmit the quantum information, and reconstruct you at a distant location. The new you would have all your memories, personality, and physical characteristics. From the inside, you would feel a seamless continuity of consciousness. You would remember stepping into the teleporter and emerging at the destination, but would it really be you? Or would it be a copy, while the original you was destroyed during the scanning process? If the original you needs to be destroyed for the teleportation to work, to avoid violating the quantum no-cloning theorem, then is teleportation really just a very sophisticated form of suicide, followed by the creation of a duplicate? These questions have no clear scientific answers. They venture into philosophy, questions of personal identity and the nature of consciousness that science may never fully resolve. Different people, reasonably, might come to different conclusions about whether they would be willing to undergo teleportation, even if it became technically possible. Has the realistic timeline. Despite all these challenges, Monroe and Olmskenk remain optimistic about the future of quantum teleportation, at least for simple objects and information. Quantum mechanics has been verified in our laboratories and thousands of others for decades. Monroe emphasizes, we've proven again and again that quantum mechanics accurately describes nature, and quantum teleportation is a direct consequence of quantum mechanics. If we want to teleport objects, we'll have to use quantum mechanics. There's no other theory that would allow it. For transmitting quantum information, which might be used for ultra-secure communications or quantum computing. Quantum teleportation is already a practical reality. In 2017, Chinese scientists successfully teleported quantum information from Earth to a satellite in orbit, demonstrating that quantum teleportation can work across distances of thousands of kilometers. For teleporting simple molecules or complex structures, the timeline extends into decades. Monroe estimates that we might be able to teleport simple organic molecules within 20 to 30 years, and perhaps more complex structures within 50 to 100 years. As for teleporting human beings, I wouldn't hold my breath, Olmskenk admits. We're talking about technologies that might be possible in a century or two, if they're possible at all. But the point is, they're not ruled out by the laws of physics. That means they're worth investigating. Chapter 5. Challenging Einstein. Is the speed of light really constant? Has the barcode of the universe while some scientists work on finding ways around Einstein's cosmic speed limit. Others are asking an even more fundamental question. What if Einstein was wrong? What if the speed of light isn't really constant after all? John Webb is an astrophysicist at the University of New South Wales in Australia who has spent years reading what he calls the barcode of the universe, patterns hidden in light from distant galaxies that might reveal changes in the fundamental constants of nature. Think about going to a supermarket and buying a package of lettuce, Webb explains. The package has a barcode on it, a series of black lines and white gaps that encodes information. We can see that there's information there, but we can't read it without a laser scanner. When the cashier scans the barcode, the laser reads the pattern of lines and gaps and tells us the price. The universe has its own barcodes, written in light. When we split the light from a distant star or galaxy into its component colors, creating a spectrum, we see that certain colors are missing. These missing colors appear as dark lines in the spectrum, creating a pattern similar to a barcode. Spectral lines and the electromagnetic force. These spectral lines are created when light passes through clouds of interstellar gas. Different chemical elements in the gas absorb light at specific wavelengths, creating the dark lines we observe. The exact positions of these lines depend on the electromagnetic force, the force that holds electrons in their orbits around atomic nuclei. From these spectral lines, we can learn many things, Webb explains. Their positions tell us which elements are present: hydrogen, helium, iron, and so on. But they also tell us something more fundamental, the strength of the electromagnetic force in that distant cloud of gas. According to the laws of physics as we understand them, the electromagnetic force is the same everywhere in the universe and at all times. It's what physicists call a fundamental constant, a number that never changes. The strength of this force determines how electrons bind to atomic nuclei, which in turn determines the exact wavelengths of light that atoms can absorb and emit. But what if this constant isn't actually constant? What if the electromagnetic force is slightly different in different parts of the universe? Or was different in the distant past? Asterisk hash 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 a disturbing discovery asterisk over the past 2 decades. Advances in telescope technology have allowed astronomers to measure spectral lines with unprecedented precision. Webb has used the Keck telescope in Hawaii to study gas clouds in the northern sky, and the Very Large Telescope in Chile to study clouds in the southern sky. These gas clouds are billions of light years away, meaning we're seeing them as they existed billions of years ago, when the universe was much younger. Asterisk, when Webb analyzed the spectral lines from these distant clouds, he found something unexpected and disturbing. Asterisk, when we look at a gas cloud from our laboratory on Earth, we see a particular pattern of spectral lines, Webb explains. But when we look at gas clouds in the southern sky, billions of light years away, the pattern is slightly different. Some lines have shifted toward the red end of the spectrum, while others have shifted toward the blue end. The relative spacing of the lines has changed, asterisk, even more strangely. When Webb looked at gas clouds in the northern sky in the opposite direction, he saw a different pattern of shifts. It was like looking at a barcode while intoxicated. He jokes. The pattern looked almost right, but subtly wrong. Hash 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 implications for the laws of physics asterisk. These shifts in spectral line positions can only mean one thing. The strength of the electromagnetic force was different in these distant gas clouds than it is on Earth today. And since light from different directions in the sky shows different patterns, the electromagnetic force may vary across space as well as time. Asterisk, when we first saw these results, we thought it couldn't be true, Webb admits. We found that when we look in one direction in the sky, the electromagnetic force appears to get weaker with increasing distance. But when we look in the opposite direction, the electromagnetic force appears to get stronger with distance. Asterisk, this is revolutionary and controversial. The electromagnetic force is what allows photons, particles of light, to hold electrons in their orbits and bind atoms together. If the strength of this force is changing, then the properties of light itself must be changing. Asterisk, and if the properties of light are changing, might its speed be changing as well? Asterisk hash 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 rewriting the equations of physics asterisk. If Webb's observations are correct, they would require a fundamental rewrite of physics. The equations that govern electromagnetism, quantum mechanics, and relativity all assume that certain fundamental constants, including the speed of light, never change. If these constants aren't actually constant, then all of these equations would need to be modified. Asterisk, if the laws of physics are different in different places or at different times, Webb notes, then we need to rewrite the fundamental equations. We need to reconsider some of our most basic assumptions about how the universe works. Asterisk, some of Webb's colleagues remain skeptical. The measurements are difficult and subtle, and there are alternative explanations for the observations that don't require changing fundamental constants. But Webb has now reproduced his results multiple times using different telescopes at different gas clouds, and the anomalies persist. Asterisk, could Einstein have been wrong? Webb asks, could the speed of light be different in different parts of the universe? The evidence suggests this might be the case, and if it's true, it changes everything we thought we knew about the cosmos. Asterisk hash hash. Chapter 6, The Varying Speed of Light, New Theory of the Universe. Asterisk hash 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 John Mageio's radical proposal asterisk. While John Webb's observations suggest that fundamental constants might not be constant after all, another physicist has taken this idea and run with it in a bold new direction. John Mageio, a theoretical cosmologist at Imperial College London, has proposed that the speed of light was much faster in the early universe than it is today. And this idea might solve one of the biggest mysteries in cosmology. Asterisk, when we look at the universe, Mageio explains, we see that it looks the same in every direction. Galaxies are distributed uniformly. The cosmic microwave background radiation is uniform. Everything is remarkably homogeneous. This is a big problem because in the early universe, there wasn't enough time for light to travel far enough to create this uniformity. Asterisk, this puzzle is called the horizon problem, and it's one of the deepest mysteries in cosmology. Asterisk hash hash hash. The horizon problem asterisk, imagine the Big Bang as a cosmic party that just started. As soon as the party begins, every guest receives an identical glass of wine. But here's the puzzle. How did the waiter have time to serve everyone? In the standard model of the Big Bang, the universe expanded so quickly that light wouldn't have had time to travel from one side to the other. Different regions of space should have had no opportunity to interact or coordinate. Yet when we look at the universe, we see that it's remarkably uniform. The temperature of the cosmic microwave background radiation afterglow of the Big Bang is the same in all directions to within 1 part in 100,000. Distant galaxies on opposite sides of the sky, which should never have been in contact with each other, have similar properties and compositions. How did different parts of the universe know to be so similar if they were never in communication? The standard solution. Cosmic inflation. Most cosmologists solve this problem with a theory called cosmic inflation. According to this theory, the universe underwent a period of exponential expansion in its first instance, specifically in the first 10 to 30 seconds after the Big Bang. During this inflationary period, space itself expanded faster than the speed of light, growing by a factor of at least 1026, that's 1 followed by 26 zeros in an inconceivably brief time. Before inflation began, the entire observable universe was compressed into a region smaller than an atom. At this tiny size, all parts of space could interact and reach thermal equilibrium. Then inflation expanded this tiny, uniform region to cosmic scales, preserving the initial uniformity. Cosmic inflation says the room stayed small long enough for the waiter to serve everyone. Miguel explains, then a mysterious magnifying force rapidly expanded the room. Everyone already had their drink, and the waiter didn't need to work very hard. Inflation has become the standard explanation for the horizon problem, and it successfully explains many other features of the universe as well. But it has one significant weakness: no one knows what caused inflation. The theory requires a hypothetical inflating field that drove the exponential expansion. But this field has never been directly observed, and its properties remain mysterious. The alternative, variant speed of light. Miguel and his colleagues have proposed a radical alternative. What if, instead of changing how fast space expanded, we change how fast light could travel? What if we don't change the rate at which the universe expanded? Miguel asks, but instead change the speed limit, the speed of light itself? This is what we call the variant speed of light theory. According to this theory, in the first instance after the Big Bang, the speed of light was much faster than it is today, perhaps infinitely faster. This ultra-fast light could have traveled across the entire early universe almost instantaneously, allowing different regions to interact and reach equilibrium. As the universe aged and cooled, the speed of light gradually decreased to its current value. In our variant speed of light theory, the waiter was able to serve drinks very quickly when the party started, because she was moving at super high speed. Miguel explains. Later, she slowed down and latecomers perceived her as moving normally. They couldn't understand how she had served so many people in such a short time. Does this theory work? Miguel's variant speed of light (VSL) theory solves the horizon problem just as effectively as cosmic inflation does. Both theories explain why the universe appears uniform in all directions, but the VSL theory has some advantages. First, it's conceptually simpler. Instead of invoking a mysterious inflating field that exists only for a brief moment and then disappears, the VSL theory simply proposes that one of the fundamental constants of nature, the speed of light, changes over time. Second, the VSL theory makes different predictions than inflation about certain subtle features of the cosmic microwave background radiation. These predictions could, in principle, be tested with future observations. However, the VSL theory also faces significant challenges. It requires modifying Einstein's theory of relativity in fundamental ways, since that theory is built on the assumption that the speed of light is constant. Miguel and his colleagues have worked out mathematical formulations that allow the speed of light to vary while preserving most of the successes of relativity. But these formulations remain controversial. Cosmic strings highways through space. If the speed of light did vary in the early universe, Miguel's theory makes another intriguing prediction. There might be remnants of that era still existing today in the form of cosmic strings. Cosmic strings are hypothetical, one-dimensional defects in the fabric of space-time, essentially cracks or seams left over from the early universe. According to the VSL theory, these cosmic strings might preserve the properties of the early universe, including its higher speed of light. Think of cosmic strings as the London Underground railway system. Miguel suggests On the surface, there's a speed limit, Einstein's limit. But underground in the cosmic string network, there's no speed limit. You might say that on the surface, Einstein's rules apply, but inside cosmic strings, there's no speed restriction at all. Asterisk, if cosmic strings exist and do indeed have regions where light can travel faster than normal, they would form natural highways through the universe, spots where spacecraft could potentially travel at superlight speeds without violating the local laws of physics. Asterisk, if we could find cosmic strings and figure out how to navigate them, Miguel speculates, we might be able to use them to travel quickly through the universe. They would be like wormholes, but instead of tunnels through space, they would be corridors where the speed limit is higher. Asterisk hash 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 finding the evidence. Asterisk, of course, cosmic strings remain hypothetical. Despite decades of searching, astronomers have not definitively detected any. There are a few candidate observations, subtle gravitational effects, that might indicate the presence of cosmic strings, but nothing conclusive. Asterisk, similarly, the evidence for a varying speed of light remains circumstantial. John Webb's observations of changing spectral lines are intriguing, but not yet definitive. Other astronomers have attempted to replicate his results with mixed success. The scientific community remains divided on whether these observations truly indicate changing fundamental constants, or whether they can be explained by more conventional physics. Asterisk, if the speed of light varies across the universe or has changed over time, Webb notes, then physics in the early universe might have been quite different from physics today. We might need to reconsider fundamental assumptions about how stars formed, how galaxies evolved, and how the cosmos reached its current state. Asterisk hash hash has the implications for space travel. Asterisk, for the purposes of interstellar travel, the possibility of a varying speed of light is tantalizing. If there are regions of space, perhaps along cosmic strings, or near certain exotic objects where light travels faster than its normal speed, then these regions might offer shortcuts through the cosmos. Asterisk, a spacecraft that could access these fast light regions might be able to cross interstellar distances in far less time than would normally be required, even if the spacecraft itself couldn't exceed the local speed of light. If that local speed is much higher than the usual 300,000 kilometers per second, the effective travel time could be dramatically reduced. Asterisk, alternatively, if we could somehow manipulate the local properties of space to increase the speed of light in a particular region, we might create artificial fast light corridors through which spacecraft could travel. This would be similar to the Alcubierre warp drive, but instead of warping space to move the spacecraft, we would be warping the properties of light itself to allow faster motion. Asterisk, these ideas remain highly speculative. We have no technology that can manipulate fundamental constants of nature, and we don't even know for certain whether such manipulation is possible. But the point is that scientists are actively exploring these possibilities using observations, experiments, and theoretical calculations to probe the limits of what physics allows. Asterisk hash hash chapter 7, the roadmap to the stars. Asterisk hash hash hash, where we stand today. Asterisk, as we've seen throughout this exploration, there are multiple potential paths to faster than light travel, or its effective equivalent. Asterisk 1. Asterisk asterisk warp drives. Asterisk asterisk, using negative energy to contract space ahead of a spacecraft and expand it behind, creating a warp bubble that can move at arbitrary speeds without the spacecraft itself moving through space. Asterisk 2. Asterisk asterisk wormholes. Asterisk asterisk, natural or artificial tunnels through spacetime that connect distant regions, potentially allowing instantaneous travel across vast distances. Asterisk 3. Asterisk asterisk quantum teleportation. Asterisk asterisk, transmitting quantum information at light speed and reconstructing objects at the destination, effectively beaming matter from one place to another. Asterisk 4. Asterisk asterisk varying speed of light. Asterisk asterisk, exploiting regions of space such as cosmic strings where light might travel faster than normal, or manipulating the local speed of light to create fast transit corridors. Asterisk, each of these approaches has profound challenges, both theoretical and practical. None of them is likely to become reality in the near future, but importantly, none of them is forbidden by the laws of physics as we currently understand them. Asterisk hash hash has the current state of technology. Asterisk, our current spacecraft technology is primitive by the standards we're discussing. The fastest human-made object, the Parker Solar Probe, travels at about 190 kilometers per second relative to the Sun at its closest approach. roughly 0.06% of the speed of light. At this velocity, reaching even the nearest star would take thousands of years. Asterisk, to put our current capabilities in perspective, asterisk, 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 Voyager 1 asterisk, asterisk, launched in 1977, has traveled about 23 billion kilometers from Earth, roughly 0.00 light years in 47 years of travel. Asterisk, at its current speed, Voyager 1 would take about 75,000 years to reach Proxima Centauri. If it were headed in that direction, the asterisk, asterisk, New Horizons asterisk, asterisk spacecraft, which flew past Pluto in 2015, is traveling at about 16 kilometers per second, fast enough to reach the moon in less than a day, but not fast enough to make interstellar travel practical. Asterisk, these speeds are impressive by historical standards after all. Just over a century ago, the fastest human transportation was the train, traveling at perhaps 100 kilometers per hour. But they're nowhere near what we need for practical interstellar exploration. Asterisk, hash, 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 the next steps, asterisk, what technologies might bridge the gap between where we are and where we need to be. Several promising developments are on the horizon. Asterisk, 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 advanced propulsion systems, asterisk, asterisk. NASA and other space agencies are researching next-generation propulsion technologies that could dramatically increase spacecraft speeds, asterisk. Asterisk, asterisk, nuclear thermal propulsion, asterisk, asterisk, uses a nuclear reactor to heat propellant, potentially doubling or tripling the efficiency of chemical rockets. Asterisk, 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 nuclear electric propulsion, asterisk, asterisk, uses nuclear power to run electric thrusters, enabling higher velocities over long periods. Asterisk, 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 solar sails, asterisk, asterisk, use radiation pressure from sunlight to accelerate spacecraft without requiring propellant, asterisk, asterisk, laser sail systems, asterisk, asterisk, such as the Breakthrough Starshot project, propose using powerful lasers on Earth to accelerate tiny spacecraft to 20% of light speed, potentially reaching Proxima Centauri in about 20 years. Asterisk, 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 better understanding of fundamental physics, asterisk, asterisk, many of the exotic technologies we've discussed, warp drives, wormholes, quantum teleportation, require a deeper understanding of quantum mechanics and gravity. Current research directions that might provide this understanding include asterisk, 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 quantum gravity theories, asterisk, asterisk, attempting to reconcile quantum mechanics with general relativity, asterisk, 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 string theory, asterisk, asterisk, and other approaches to unifying all fundamental forces, asterisk, 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 experimental tests, asterisk, asterisk, of quantum mechanics at larger scales and in stronger gravitational fields, asterisk, 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 searches for dark matter and dark energy, asterisk, asterisk, which might reveal new forms of matter and energy that could be harnessed for propulsion. Asterisk, 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 detecting and studying exotic phenomena, asterisk, asterisk, if wormholes, cosmic strings, or regions of varying light speed exist in nature. We need to find them before we can exploit them. Asterisk, 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 gravitational wave detectors, asterisk, asterisk, like LIGO and future space-based detectors, might detect signatures of cosmic strings or wormholes. Asterisk, asterisk, next-generation telescopes, asterisk, asterisk, will allow more precise measurements of spectral lines from distant objects, testing whether fundamental constants truly vary. Asterisk, 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 particle accelerators, asterisk, asterisk, and quantum experiments continue to probe the limits of our understanding, potentially revealing new physics. Hash, 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 the timeline, asterisk, realistically, how long might it take before humanity can travel to the stars? This is impossible to predict with certainty, but we can make some educated guesses based on the current state of knowledge. Asterisk, 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 near term to 05 to 050, asterisk, 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 continued development of advanced chemical and nuclear propulsion systems, asterisk, possible demonstration of laser sail technology with tiny probes, asterisk, further refinement of quantum teleportation with increasingly complex molecules, asterisk, better measurements of potential variations in fundamental constants, asterisk, possible first detection of gravitational waves from cosmic strings or other exotic objects. Asterisk, 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 medium term to 050 to 100, asterisk, 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 possible launch of interstellar probes using laser sail or other advanced propulsion, capable of reaching nearby stars in 50 to 100 years. Asterisk, demonstration of more sophisticated quantum teleportation, perhaps of simple biological molecules, asterisk, better theoretical understanding of quantum gravity, possibly revealing new physics relevant to warp drives or wormholes asterisk if cosmic strings or other exotic phenomena are detected. Initial studies of their properties asterisk 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 long-term to 100 to 20 asterisk asterisk asterisk. Possible development of fusion-powered spacecraft capable of reaching 10 to 20% of light speed asterisk if warp drive or wormhole physics proves feasible. Initial experimental demonstrations on microscopic scales asterisk more sophisticated quantum teleportation systems, possibly approaching the complexity needed for macroscopic objects asterisk if regions of faster light speed exist, possible attempts to access and utilize them asterisk 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 very long-term to 1,000 to 100 plus asterisk 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 possible development of practical warp drives, traversable wormholes, or other faster-than-light technologies asterisk human expansion to nearby star systems asterisk establishment of interstellar civilization asterisk. These timelines are highly speculative and depend on numerous unknowns. Future scientific discoveries, technological breakthroughs, level of investment in space exploration, and even human survival and prosperity over the coming centuries. The timeline could be much faster if we make unexpected discoveries, or much slower if current theoretical approaches prove to be dead ends. Asterisk hash the philosophical perspective asterisk beyond the technical challenges. Humanity's journey to the stars raises profound philosophical questions. What does it mean to be human in an age where we might remake ourselves, to survive in alien environments, upload our consciousness into machines, or teleport our bodies across light years? How do we maintain our humanity while adapting to the cosmos? Asterisk these questions don't have clear answers, but they're worth contemplating as we push toward the stars. Space exploration has always been about more than just technology. It's about expanding human knowledge, challenging ourselves, and securing our long-term survival as a species. Asterisk Carl Sagan once wrote, "The Earth is a very small stage in a vast cosmic arena. The Earth is the only world, so far, to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand." Asterisk, but Sagan also believed that this situation is temporary. Humanity's future, if we survive our current challenges, lies among the stars. The technologies we've explored in this article warp drives, wormholes, quantum teleportation, and manipulation of fundamental constants represent possible paths toward that future. Asterisk hash conclusion, the unquenchable human spirit asterisk throughout human history. We have consistently pushed beyond boundaries that once seemed absolute. We crossed oceans that appeared endless, built flying machines that defied gravity, split atoms that were thought to be indivisible, and walked on the surface of another world. Asterisk each of these achievements required overcoming not just technical challenges, but also conceptual barriers, the limits of what people believed was possible. Before the Wright brothers, powered flight was considered impossible by many serious scientists. Before atomic energy, the idea of releasing the power locked within atoms seemed like fantasy. Before Apollo 11, landing humans on the moon was science fiction. Asterisk the journey to the stars represents humanity's ultimate frontier. The distances are so vast, the challenges so profound, that it's easy to dismiss the entire enterprise as impossible. But as we've seen, the laws of physics as we currently understand them don't absolutely forbid faster than light travel or its equivalent. They just make it extraordinarily difficult. Asterisk warp drives are consistent with Einstein's equations if we can harness negative energy. Wormholes could exist if we can stabilize them. Quantum teleportation is already demonstrated for simple systems and might scale to more complex objects. The speed of light itself might not be as constant as we thought, potentially offering new routes to the stars. Asterisk none of these paths is easy. All of them require scientific breakthroughs that may take decades or centuries to achieve, if they're achievable at all. But the point is that we're exploring them, using rigorous scientific methods to probe the limits of what's possible. Asterisk scientists like Miguel Alcubierre are working out the mathematics of warp drives. Experimentalists like Steve Lamoreaux are creating negative energy in laboratories. Quantum physicists like Chris Monroe and Steve Lamoreaux are teleporting atoms. Cosmologists like Joe Maggio are questioning whether fundamental constants are truly constant. Astrophysicists like John Webb are reading the barcodes of distant galaxies, searching for evidence that the laws of physics themselves might vary. Asterisk, this is how progress happens not through sudden revolutionary breakthroughs, but through the patient accumulation of knowledge, the gradual refinement of theories, and the persistent exploration of possibilities. Each small advance builds on previous work, and occasionally, these incremental steps lead to transformative changes in what we can achieve. Asterisk, we cannot predict exactly how humanity will ultimately reach the stars. Perhaps it will be through warp drives, bending space itself to circumvent the light-speed barrier. Perhaps we'll discover natural wormholes left over from the Big Bang, and learn to traverse them safely. Perhaps we'll master quantum teleportation and beam ourselves across the cosmos as patterns of information. Perhaps we'll find cosmic strings or other exotic structures that offer fast lanes through space. Or perhaps the solution will be something we haven't even imagined yet, a breakthrough that awaits a future Einstein, or a discovery that rewrites our understanding of reality. What we can say with confidence is this: if we continue to explore, experiment, and push the boundaries of knowledge, we will eventually find ways to expand beyond our current limitations. The universe is vast, but human creativity and determination are also powerful forces. Asterisk, the stars have beckoned to humanity since the first humans looked up at the night sky and wondered what those points of light might be. For most of history, we could only dream of reaching them. But now, for the first time, we can at least imagine realistic paths, however challenging that might someday take us there. Asterisk, that journey begins with the work being done today in laboratories and observatories around the world by scientists who refuse to accept that anything is truly impossible until it's been proven so beyond all doubt. Their work is laying the foundation for technologies that might not mature for generations, but which could ultimately transform humanity from inhabitants of a single world to citizens of the cosmos. Asterisk, the road to the stars is long, and we've only just begun to travel it. But if history teaches us anything, it's that humanity has never been content to stay in one place, to accept boundaries, or to believe that any frontier is truly final. The same restless curiosity that drove our ancestors to cross continents and oceans now drives us to reach for the stars. Asterisk, we may not get there in our lifetimes, or even in our children's lifetimes, but someday, perhaps in a century, perhaps in a millennium, our descendants will look back at this era as the time when humanity first seriously grappled with the question of how to break the light-speed barrier and claim our place among the stars. They will remember the physicists who first demonstrated negative energy, the theorists who worked out the mathematics of warp drives, the experimentalists who first teleported atoms, and the astronomers who first questioned whether the speed of light was truly constant. Asterisk, and when they finally stand on the surface of an alien world, circling a distant star, looking up at an unfamiliar sky, they will know that their journey began with people who dared to ask, what if we could travel faster than light? What if the impossible is merely very, very difficult? Asterisk, the universe is vast, ancient, and filled with wonders we have only begun to glimpse. Somewhere out there might be other civilizations who have already solved the problems we're struggling with, who have found ways to traverse the cosmos and become true citizens of the universe. Or perhaps we are among the first pioneers in a young universe, and it will be humanity that blazes the trail to the stars. Asterisk, either way, the journey is worth taking, not just for the practical benefits, the resources, living space, and security that a spacefaring civilization would enjoy, but for something deeper. The quest to reach the stars is fundamentally about understanding our place in the cosmos, pushing the limits of what's possible, and refusing to accept that any realm, however distant, must forever remain beyond our reach. Asterisk, as we've seen throughout this exploration, the path to faster-than-light travel is fraught with challenges. We must harness exotic forms of energy that may barely exist. We must warp the very fabric of space-time. We must learn to manipulate quantum entanglement on scales far beyond anything we've achieved. We must question fundamental assumptions about the nature of reality that have been taken for granted for a century. Asterisk, these are daunting tasks, but they are not impossible. The laws of physics, as best we understand them, do not absolutely forbid what we're trying to achieve. They merely tell us that it will be extraordinarily difficult, which is exactly the kind of challenge that has always brought out the best in human ingenuity and determination. Asterisk, so we continue the work. We continue to explore, to experiment, to theorize and test. We build better telescopes to peer deeper into space and further back in time. We construct more sensitive detectors to measure the tiniest quantum effects. We develop more powerful computers to model exotic physics. We train new generations of scientists and engineers to carry the work forward. Asterisk, and perhaps, someday, all of this effort will pay off. Perhaps someday a spacecraft will engage its warp drive and slip through space-time at superluminal velocities, crossing light years in days or weeks. Perhaps explorers will step through a stabilized wormhole and emerge in orbit around a distant star. Perhaps quantum teleportation will advance to the point where we can beam ourselves across the galaxy as easily as we now send an email. Asterisk. When that day comes, if it comes, humanity will have achieved something truly extraordinary. We will have overcome not just a technical barrier, but a fundamental limitation of nature itself. We will have proven that intelligence and determination can triumph over seemingly insurmountable obstacles. We will have earned our place as citizens of the cosmos, no longer bound to a single world, but free to explore the infinite wonders of creation. Asterisk, that is the promise that drives the work we've explored in this article. That is why physicists spend decades in laboratories trying to create negative energy. Why cosmologists question whether fundamental constants are truly constant. Why theorists work through page after page of complex mathematics to explore the implications of warp drives and wormholes. Asterisk, the stars are waiting. The universe is vast beyond comprehension, filled with mysteries and wonders we can barely imagine. It may take us generations or even millennia to develop the technologies we need to explore it. But make no mistake, we will get there. Because that's what humans do. We explore. We discover. We push beyond every frontier we encounter. Asterisk, the impossible is just what we haven't figured out how to do yet. And eventually, with enough time, creativity, and persistence, we figure it out. Asterisk, the journey to the stars has already begun. Every experiment that probes the limits of quantum mechanics. Every observation that questions our understanding of fundamental constants. Every theoretical paper that explores exotic space-time geometries, all of these are steps on that journey. Asterisk, we are laying the groundwork for a future we may never see. Building knowledge that will be used by people who haven't yet been born to achieve things we can barely imagine. This is humanity's greatest strength, our ability to work toward goals that extend far beyond our individual lifetimes, to contribute to projects that may take centuries to complete. Asterisk, the stars have beckoned to us since the dawn of consciousness. For most of human history, they were nothing but distant lights in the sky, beautiful, mysterious, but forever unreachable. Now, for the first time, we can see a path, however long and difficult, that might lead us to them. Asterisk, that path begins here, with the science we've explored in this article. It continues through decades or centuries of additional research, technological development, and gradual progress. And it ends, or rather, it takes a new beginning among the stars, with humanity finally taking its place as a truly cosmic species. Asterisk, the road is long. The challenges are immense, and success is far from guaranteed. But one thing is certain, we have to try, because reaching for the impossible, pushing beyond every boundary, and refusing to accept limitations, that's what makes us human. Asterisk, the universe awaits, and someday, somehow, we'll find our way there. Asterisk, through the warp and weft of space-time, across gulfs measured in light years, beyond every horizon, and through every barrier we're coming. It may take us another 100 years, or another 1,000, but make no mistake, we're coming. Asterisk, because that's what explorers do, and humanity, at its core, has always been a species of explorers. Asterisk, the stars are calling, and we will answer. Asterisk, if you enjoyed this journey through the cutting edge of physics and the quest to reach the stars, please subscribe to our channel and hit the notification bell so you never miss our latest videos on space exploration and breakthrough science.